Welcome to day 2. We're going to be going over graphs of exponential and logistic functions. So in the last video we went over kind of what exponential and logistic functions were and maybe how to answer some questions that involve them. Today we're going to be focusing just on what they look like, so what their graphs look like. So we'll start off with the graph of f of x equals 2 to the x, and we'll just kind of plot some points. So I'm going to let x equals 0, so 2 to the 0 power is going to be, our marker's not working. Here we go. Okay, so I got 1 when I'm at x equals 1, I'll be at 2, x equals 2, that's 2 to the second, and 3, that'll be to the 8th, which I can't see because the smartboard isn't bright enough to actually let me see the grids. And then I got a couple points going right there. And the thing about this 2 to the x, it can never equal 0, and it can never go negative. So we actually have a horizontal asymptote right there. And so we basically have this line that goes like this. So if I'm looking at this, my range is that y is going to always be greater than 0, but not equal to. Domain is all real numbers. It's continuous because I never have to lift my pen up. It has no symmetry. Bounded. So remember, bounded means like, is there ever a point where it doesn't go above or below a certain y value? And so it is bounded at, let's see, y equals 0, and we should say it's below, because it could be bounded above. It has an asymptote at y equals 0. There are no extremes, so no mins or maxes on this thing. Now for the end behavior, we have to kind of think about this. All right, so let me scroll up a little bit here. One of the things that we could do when we have x approaching infinity, we can actually just kind of plug it in and see what happens. So if I do 2 to the infinite power, that's a big number. That's just basically infinity. So I know that y is going to go towards infinity. But when I plug in negative infinity, okay, so this is, remember the negative exponents will bring it to the bottom. So now I have 1 over an infinitely large number. That's going towards 0. And so here I can see the end behaviors, which I've confirmed on the graph already, but as x is going towards the left, y is going towards 0, and as x goes up towards the right forever, y is going up forever. So when we're looking at this kind of basic function, a times b to the x, we have some features of it that I just have summarized here, I guess. I don't know. If your b value is greater than 1, then your exponential function is going to be growing. It's going to be getting larger. So just like the one that I had up above graphed. If your b value is less than 1, then it's actually going to be called a decay factor, and it's going to get smaller and smaller and smaller. And this is all remembering that b has to be greater than 0, and b is not allowed to equal 1 in particular. So if b were to go negative, the graph does this really weird alternating thing, because sometimes you'll get an even power, which would make the negative positive, and sometimes you'll have an odd power, which will make it negative. And it does this very weird jumping back and forth with points that looks really weird when you do it. So there's a special case down here, which is f of x equals e to the x. So e is this natural base. It's this number that occurs in real life all the time. This weird little limit notation over here we'll learn eventually at the end of the year, but if you kind of do this, this number kind of rapidly approaches 2.718-ish, which is what the mathematical number e is. Now, when we go to plot this type of one, it's really, we can't plug in points like we did before, really, because I don't know what e to the first is, or e to the second, or e to the third. So we really just plot a single point, which is the y-intercept, and the asymptote, and then we just make the exponential shape for it. So when you have e as your base, we really can't do much more than plot a single point, which is when the exponent equals 0, and we'll go from there. All right, so let's see what's on the next page. Oh, cool. So we'll do an example real quick. So if you feel like you got this, maybe try graphing it yourself, and then you can check the answer key online to see if you got it right, or you can keep watching. I'm going to go over 2 different ways of solving this one. So I'm going to graph it first using transformations, just to kind of show you how to do that. So first I'm just going to remind you, even though we just did this, how I might do this base function of 2 to the x. So I have an asymptote, when it's at 0, I'm going to be at 1. Then I'm going to do 2 to the first is up 2, 2 to the second is up 4, and then up 8. And then I can go backwards to a half and a fourth. So I'm going to use that to kind of help me. But the first thing I'm going to do is take care of the fact that I have this x minus 1 and the whole thing plus 2. That's actually going to make these little fake axes. So I'm going to draw these little fake dotted lines. So they're not dashed, so I'm not drawing an asymptote. But I'm going to pretend like these dotted lines here are my new axes. Okay, so I'm going to graph from these dotted lines. I'm just going to do -3 times 2 to the x. So if I go to do that, this -3, so the negative is going to reflect it vertically, and the 3 is going to stretch it. So this first point, which would normally be, I'm just going to graph with a normal graph. So it would be down 1, down 2, down 4, and then down 8, which I think is right around there. So now, instead of going down 1, down 2, down 4, down 8, I'm going to multiply those by 3. So let me use a different color for that. So instead of down 1, I'm going to go down 1, 2, 3. So that's a point. Instead of down 2, I'll go 1, 2, 3, 4, 5, 6. So I'm just multiplying each of these heights by 3. Next one would be down 12, which is all the way down there. And if I went backwards with the green points, I would have been, what would that be? Down a half. So now I'm going to be down 3 halves. So that's 1.5. And then I think I would be somewhere around there. So this is what this graph is going to look like. So you can kind of see, like, using these fake axes, which are called the transposition of axes, I can actually graph it relatively easily, as long as I know this parent function, this 2 to the x, as long as I know that really well. Now, some people hate what I just did, so I'm going to show you the alternative way, which uses tables. I'm going to pick numbers. What I really want to do here is just start off with the basic one. Okay, so I'm going to let y equal the base function, which is 2 to the x. And if I do that, let's see, I get 1/4, 1/2, 1, 2, and 4. And what we're going to start doing is just building what g of x is. So I'm going to take this exact thing over here, but I'm now going to multiply it by -3. So my x values stay the same. My y values are now going to be multiplied by -3. So that's going to give me a -3/4, a -3 halves, a -3, a -6, and a -12. And what I want to do now is add the last little bit in, which is the x minus 1 and the whole thing plus 2. And you have to remember that x is backwards. So even though it says x minus 1, I'm actually going to add 1. And then I'm going to take that y values that I had up there, and I'm just going to add 2 to every single one of them. So I do -2 plus 1, so that's -1, 0, 1, 2, and 3. And then now I'm just going to line up the next. I'm going to do a -3/4, so I need to add 2 to that. That gives me like 1.25, I think, when I do it. This one's going to give me 1/2, -1, -4, and -10. And now I can just plot these points. So I don't care which way you like to do it. The tables take longer, but if you have a really hard time doing what I did with the transposition of axes and kind of using my knowledge of what 2 to the x looks like, then perhaps this would be better for you to use the tables. And let's see, example 2. So now we just do the exact same thing using E, and this one I would strongly recommend we don't use tables. And we do use a transformation. So I'm going to apply these transformations, which is to the right 1 and up 2. I'm just going to put those little dotted lines there again. And I still can't see it because my smartboard's not bright enough, so you can see that I'm missing a lot. Good job. Now, the first point that I would, first point I would normally graph would be on the line up 1. Okay, so that would be e to the 0 power if I didn't have anything else going on. And then I would just normally graph that line. But what I'm going to do is multiply that by -3. So from here, okay, I'm going to go down 1, 2, 3, and here is that first point now changed. And for E, I really can't graph any other point. So I'm just going to draw my exponential shape. Remember that we always need to include the asymptote drawn in there. The asymptote is part of the graph. It has to be drawn there. Alrighty. That was fun, right? Woo! Logistic functions. They have a pretty neat little graph here. So, let's see here. I'm going to change the scale of this graph because it just doesn't work for what I have going on here. So you might remember from yesterday's lesson that this top number is the limit to growth. So that's the biggest this can ever be. So I'm going to let that be way up here. Okay, so I'm going to let this be y equals 1, this is y equals 0. And if I let x equal 0, this is going to be 1 over 1 plus e to the 0, so 1. So this is going to be 1/2. So the y-intercept is going to be right here, and this graph kind of goes like this. Okay, and I'm going to confirm that that's what it looks like with you when we start filling out this end behavior business over here. But if I just use that graph, its range is that it's between 0 and 1, but it can never equal them. The domain is all real numbers. It is continuous. It actually is symmetric, but not around any normal point that we're used to. It's actually symmetric about the point 0, 1/2. So this kind of point right here, it's symmetric about that. It is bounded both above and below. So above it's at y equals 1, and below it's at y equals 0, which also happen to be the asymptotes. And the end behavior. So we're going to do that same thing that we did before, which is I'm going to kind of let x equal this infinity and kind of see what happens. So if I do that, I get that. Now, e to the negative infinity, that's really a 1 over e to the infinite power, which is 0. Okay? So this whole term right here, it basically is equal to 0, and I have 1 over 1. So I'm going to have that y is approaching 1 as x is going towards infinity. If I plug in negative infinity, I'm going to get 1 over 1 plus e to the now positive infinity. And that's an infinitely large number, so this ultimately ends up becoming 1 over an infinity, which is actually just 0. So y is approaching 0 when I go to the left. So that's how I knew that my end behavior on this side, over here, was approaching 0, and on this side, it was approaching 1. So I'll do an example graph of this, just so that we can kind of see what the process we follow is. Basically, we find the y-intercept, so I'm just going to do let x equal 0, so I'll have 8 over 1 plus 3 times 0.7 to the 0 power. So this part right here is just going to equal 1. Anything to the 0 power is 1. So I have 8 over 1 plus 3, 8 over 4, or 2. My horizontal asymptote. So really cool thing about these. They always have 1 at 0, and they always have 1 at the limit to their growth, which remember is the top number. So I can use that to help me graph it now. I'm going to change the scale of this to be, I think, so my y scale, that says scale. I don't even know what that says. Whew. My y scale I'm going to let be times 2. So I have a y-intercept at 2, 2, 4, 6, 8. So I have a horizontal there, horizontal there. And what I really need to do is, I'm not sure whether the graph's going to go like this or whether it's going to go like this as it approaches those asymptotes. Okay, so what I need to do is just do a quick check of at least one of them by plugging in infinity. So if I do 0.7 to the infinite power, and this gets a little bit tricky here. So this is actually, since it's a number less than 1, it's getting smaller. So this tends towards 0. Which means that this whole thing is really just going to be an 8 over 1 plus 3 times 0, or really just 8. So when x is approaching infinity, y is approaching 8. Infinities and 8s, they look so similar. So I actually know that I'm going this way, and then because I know what the logistic function looks like, I know that it's going to go this way on the other side, so I don't have to bother checking its end behavior. Alrighty, moving along here. Whew. These ones are going to be tough for us to do, but we're going to manage. So we're going to use this data and we're going to do the regression in our calculator. So it said that we're going to use exponential regression for this one, so I'm looking for y equals a times b to the x. And I want to try to predict the population for 2003. Now, when we're doing these with years, it's just really obnoxious to actually use these kind of large numbers, so we actually let this start at 0. So I'm really going to graph these numbers here all the way up till I think 100. That's what I'm doing, and then I'm going to put this in L1 and this in L2. So I'm going to jump over to the calculator and do that, hopefully not too painfully slow. But remember, we'll go to Stat, Edit. If you have anything in there, you just go up top and you hit Clear. Don't hit Delete. Now, all right, I'm back after some technical difficulties. My calculator decided to break. So just to kind of summarize, because I don't know if I'm editing this or not, who knows. But I'm creating an exponential regression in my calculator, so y equals a times b to the x. I'm doing years versus population. I don't want to actually enter the years because they're too large, so I let the first one be t equals 0 and then just follow it along. So we went to our calculator, we hit Stat, Edit. If you already have numbers in here, you just hit Clear, and that would clear them out. So I just entered the numbers in so you don't have to listen to me talk. Then I go to Stat, back to Stat. I'm going to go to Calculate this time, and I want to go down to one of the ones that says Exponential Regression, so number 0, right here. Too far. 0. I want list. I don't have a frequency. I want to store it. So remember, we store it by going to vars, over to yvars, into this function, and putting y1 in there. Now calculate. Blah, blah, blah. So there's my actual equation that I have there, and it graphed it for me. Okay, so I'm going to do zoom, let's think here. I think I want to do zoom stat, because I think that will give me a nice window. We'll see if it actually works. It didn't at all. So I'm going to pause it. So remember, you hit on, you can pause it. I'm actually going to turn my plots on so I can actually see the graph, and now I'm going to try to do zoom stat. So there's my actual graph. Ooh, slow motion here. So the reason I'm making us do this is because we can actually use this to estimate. So population in 2003, which is what this question is actually asking us to do, I should just be able to hit trace, and then if I hit the down arrow, I move to the equation itself instead of the plots, and I should be able to hit 103, which would be the year 2003, and I can actually get my answer right there, 304. So if I want to do the next one, the logistic function, I'll just do the same exact thing. I'm going to go into Edit. I'm going to clear these. This one will hopefully not take too long for us. I'm just going to enter these numbers. So I got 5, 10, 15, 20, 25, and then I have 100, 180, 270, 300, 305. And you can kind of see these numbers are tapering off a little bit. And that is because we have a capacity, so we have a limit to the growth. So that tells us that this is probably going to be a logistic function. So I'm going to actually just clear my y1 real quick, do zoom 9 so I can see what this looks like. You can see that it kind of follows this shape. If I draw on this and hope that the computer doesn't break, it kind of follows that limit to growth that we got going on there. So we're going to make this regression real quick. So I'm going to go to Stat, Calculate, and you can see that there is a logistic regression. This one takes a long time normally because it has to think about it a lot. I'm going to store my answer real quick. Yvars, function, there we go. Calculate. So while it's thinking about this, all I'm going to do is actually just look at this equation. It's asking me what is the carrying capacity, so there's a maximum. And the way that this function is written is C is on top, and C is 314. So that means that this thing can only handle a temperature of 314.79 degrees. And that is the end of the question. So yeah, let me know if you have any questions or anything. That's the end of this video, and I will see you later.